Hello everyone. So in the previous class, we were discussing about maxima and minima, and the goal of discussing maxima and minima was we want to perform optimization. Okay, I hope you can see what I have written on the white sheet, isn't it? Is it visible? Yes.
Yes, sir, it's visible, sir.
All right. So optimization. See, we learned how to make a neural network. We also learned how it performs a training or a learning. And as per the working of a neural network, we know at the last layer it gives output. Okay, that we say as Y prediction. And we are having Y actual also. Okay, then what we do is, because we are training, we are making this neural network to learn. Why? We want this AI model to give predictions as likely as what a human do. Okay, so the thing is here, whatever be the outcome which we got from the model, we do calculate error. Okay, that means yp minus ya. This is called as an error. Okay, and here I called it as E equal to yp minus ya. And then I want to convert this thing into high order. Why? Because ultimately I need to perform the optimization. And doing optimization means I need to reduce this error. And the way to reduce the error is I need to adjust weight and the bias, that you know that weight and the bias are the parameters, and they are the only learnable or trainable parameters in a neural network. Okay, so reduction of error totally depends upon how you tune your parameters. And tuning the parameters, obviously, you need to differentiate this error with respect to those parameters. Especially, we do take like the differentiation, partial differentiation with W. Okay, for that, I require high order term, high degree term. Okay, so I am going to square my this error term, so that will be like yp minus ya ka whole square. Okay, and then later on what I did is I perform the summation. That means let us consider all the errors which are present in your data. Okay, and take the mean. Okay, so this is called as MSE, mean square error. Fine, and we have to perform del E by del W. Okay, that's what we have to do. We have to differentiate this error with respect to weight, partial differentiation. And we have seen this thing in our backtracking process. Okay, backtracking, we did perform the gradient of the errors with respect to weight, and with the substitutions and all, that was a kind of maths which was a bit complicated as we go back every layer by layer. Okay, and there the formula which we have applied to update the weight was W equal to W dash is equal to W minus alpha del L by del W. This was the formula where this W is the old weight, this is the new weight, this is the learning rate, and this is your gradient. And ultimately, in the previous class, now we were discussing about gradient descent. Okay, gradient descent with maxima and minima. That's what I was teaching. And what you have seen in the gradient descent was that, sir, we want to go down. Okay, we want to go down. That means we are present at this particular point and we need to continuously calculate the gradients, and we have to find those points where error is less, and we are looking forward for minima because we want to minimize the error. So we are looking forward for minima. There are many minimas present in your polynomial, okay, where you may get minimum values. For example, the kind of curve which we have seen in our previous example was something like this. So this is also minima, this is also minima, this is also minima, this is global minima. If you reach a global minima, then that's the perfect thing which you have achieved. Okay, so uh, we do try and iterate and look forward for the minimas, and obviously this is a process, optimization process, where moving from one point to another point requires a maths, and the kind of maths which is used here in a general case is this, that is the updation of the weight, and we will see further more techniques for the optimization ahead. Okay, then I also taught you about early stopping, one of the concept. That means you are training your model, and at a particular iteration I got certain score, and after that what happened is I am not improving in the scores. So in that particular case I don't want to iterate further. Okay, so that was your early stopping, where you are going to stop after some iterations by keeping patience. Okay, if you are not improving in the training, fine. So for that I have also created a code. Let me tell you how to perform that early stopping implementation. Now I'm sharing the entire screen, you can see. Okay, this is the code for early stopping. Okay, so let me increase the screen also. Here I am taking the basic or the fundamental libraries which you know, TensorFlow, Keras. Okay, and in TensorFlow, in Keras I am having callbacks. I hope you can see this callbacks thing. Okay, and this
Sir, can you zoom little bit, sir?
okay, fine. Let me increase further more size of the Jupyter notebook. Okay, fine. So here you can see callbacks, which is present in Keras. This callbacks will provide you early stopping. Okay, here is early stopping. There is one more thing, model checkpoint. You know what happens? Every iteration, the model got trained, weight and the bias got adjusted. Okay, it depends upon you whether at a particular iteration, whatever be the changes occurred, if you want to save it, you can. That's what you can do. Okay, so for that I am having a model checkpoint also. Then later on I am having sequential model. I am introducing dense layer. Load iris, you very well know, it's a data set. Train test split, because training and the testing we want to perform. Then standard scaler, as we know that in deep learning we do scale the data and then we give it to the model. And then because this is a multi-classification task, Iris is having three classes. It's a multi-classification. I'm using label binarizer also here, that can perform one hot encoding of the data. Okay. In case of one hot encoding, what we can do is we can create separate columns for the outcomes. Okay. Now, what does that mean? Let me show you here. See, we are having a data set. Now, this is our erase data set. Okay. In erase data set, we are having a target, and these are the features. We are having four features in the erase data set. All are the dimensions, all are related to the length. Okay. And the target, this Y, we are having as versicolor, setosa, and virginica. Three classes we are having. In the previous my course, I did told you that because this is a classification problem, okay, so you can perform cross entropy, okay, for calculating the losses. That's what you can do. Cross entropy. I taught you. Okay. Here there are alternative ways also in which what I can do, label encoding, not label, one hot encoding actually they have mentioned. One hot encoding. What happens in one hot encoding is we can create separate columns for each and every outcome. This is your data, okay, and you are having three outcomes: versicolor, setosa, and virginica. So what you can do is, this is a column for versicolor, this is a column for setosa, and the third one is for versicolor and setosa and virginica. Okay, so versicolor, setosa, and virginica, this is called as one hot encoding. That means जो टारगेट है, ओके, उसको ही आप कन्वर्ट कर दीजिए इन कॉलम्स. So wherever I am having versicolor, at that places setosa and virginica will be 0. Wherever I am having setosa, there versicolor and virginica will be 0. And where I am having virginica, there versicolor and setosa will be 0. So this is what I did. It is called as one hot encoding. Okay. Actually, we can encode our data. That means convert your non numerics into numerics. That's what you can do in case of encoding. Okay. So here I am converting your non numerical value. That means three classes into numerical. Okay. Either we can do label encoding. Label encoding means giving versicolor as 0, setosa as 1, virginica as 2. This is label encoding. But I don't suggest you this thing, label encoding. Label encoding is been given now when you think that they can be represented in a form of a label, one above the other, something like that. For example, I am having low, medium, and high. This can be encoded with a label encode. Why? Because low is 0, medium is 1, high is 2. But here color of a flower can't be represented in this particular format. ये कोई label नहीं है. ओके, कि मैं एक के ऊपर एक जमा दूं, या मैं इसको जो है इस तरीके से, इफ आई एम गोइंग टू रेफर लाइक दिस 0 1 and 2, नो. The better thing is you can perform one hot encoding, and it's not only the case that you are doing this thing for only target column. No, that's not only the case. आपके पास इन फीचर्स भी, if you are available with the data, you do perform one hot encoding. Okay, so in this particular code I have been mentioned the same thing here. Okay, label binarizer, okay, is been used here, that will be performing the one hot encoding. So here let us load the data. After loading the data, you perform the scaling, then you are performing the encoding of your data. Okay, label binarizer, that means converting labels to one hot encoding. That's what I have shown you just recently. Fine. And then you can split your data into training testing. Okay, and here you are making your architecture. So in this architecture, you are taking one dense layer, two dense layer, and three dense layer. Okay, you are taking three dense layers. Fine. And in this three dense layers, the number of neurons are 10, 10, and 3. Okay. And you very well know about the activation functions. We have already learned ReLU, and the Softmax, because it is multi-classification problem. So you are taking Softmax at the last. Okay. And then you are compiling your model in order to configure it. And I have already told you that in configuration, because developing just an architecture is a non-active infrastructure, but when you configure your model, okay, so in this particular case, how this model is gonna work, that will be assigned. So we have to compile our model. In compilation we give Adam as an optimizer. This is the loss, how they will be calculated, that means predicted minus actual. Okay, and this is the evaluation, because it's an classification problem, so evaluation will be accuracy. Okay, before that I want you to show what is this why one hot encode is. What is this your value of the variable? So let me have print to it. Print y underscore one hot. Okay, so again I'm running the code. Okay, let me run the code. Fine, here it is. You can see 100 100 100. That's what I shown you here. You can see my notes. What I show you here, 100. Okay, so for the initial entries, one of the flower is present, so rest of the flower will be 0. Okay, and then in the previous entries, for example, if I go down from here, yeah, from here, the middle flower is present, so rest two are 0. And then go down further, here it is 0 0 1. So that's what I have shown you. Okay, so this is called as one hot encoding. Fine, and that's it. Okay, and what I'm doing, callbacks, including callbacks, early stopping. Okay, I am going to monitor the loss, because training will be going on, and I will be monitoring the loss. If the losses are not getting less, for example, what happened after 10 iterations? Okay, let me explain you this thing. After 10 epos, okay, loss is 0.032. Then at 11th, 12th, 13, 14, 15, we kept patience for 5 more iterations, and the losses are not going down than this. Okay, in that particular case, what we can say is kindly stop. Okay, don't further train, because the losses are not getting less and you are wasting your time. That means you are looking forward for an optimal point, and you have reached to a particular point. Below that you are unable to go down, you are unable to reach here. Okay, so if I continue my training, still I have kept patience for 5 iterations and I found that you are not improving, so certainly I think I should break this process. Okay, so it's what explained here in your early stopping. Okay, if you are having further more iterations left, come on, stop it. And whatever be the best trained weights during the training, they should be saved. For example, you have trained your model for 10 iterations. The best weights where the model give highest accuracy and the low loss, that weight will be saved. That is called as the best weight. Best model neuron weights. Okay, and it's done by using model checkpoint. So here I am having model checkpoint best iris model dot h5. Dot h5, that's an extension, okay, by the help of which I can save a file, trainable file, in my system. Okay, so this is for saving a deep learning model. In machine learning model, I hope the people are present here who are part of my previous classes. They know that we do use pickle, joblib, some of the libraries to save the model, machine learning model. Okay, dot pkl, dot joblib. Okay, so these are some scrambled files. Okay, you can say like a hosh posh or a kind of a file, trained file, which we can't understand. This is machine understandable only. Okay, it comprises of the detail, the best weights, the best trainable weights. It is present here in this particular file. Later on, we can use this file to perform further predictions. Okay, fine. That's it. Now you are going to train it. History. Train your model, and after training, here it is. We perform training for 10 iterations. Okay, in case if the accuracy is not increasing, then stop. Okay, then we can stop. So so here I trained for 10 iterations, and for 10 iterations the validation accuracy I'm getting 0.467 point, okay, 46767 here up till 4 I got. If I do run this code again, for example 20 epos, let me run this code for 20 epos, and I'm deleting this line. Just I included this line to show you how one hot encoding looks like. So let me run this code again for 20 iterations. Okay, so fine. Here, okay, one, two, three, four, five. Till five iterations, I kept patient. Okay, I was keep quiet for the five iterations. I was continuously monitoring validation accuracy. That came to be 0.7667. Then later on, it changed to 0.80. If it haven't changed to something else, then that will occur an early stopping. I should be stopping here. Why? Because after keeping the patience, okay, let me do one thing. Let me keep patience for only two times. Sir, don't keep so much patience, sir. Only two times you keep the patience. Okay, now again let me run the code. Okay, I have again run the code. Okay, and what I found here is, hmm, here the accuracy is 0.80, 0.80 still the validation accuracy. That's what I'm monitoring, the validation accuracy. Okay, validation loss actually. I put here validation loss. It's better. I should have put here validation accuracy. Accuracy. Okay, there's a change in early stopping. I'm going to monitor validation loss. Okay, just do a change. Sorry, validation accuracy. Okay, that's what the change we have to do. Let me run the code again. Hmm. Now you can see. I told that kindly keep patience for only two iterations. So you know what happened? At iteration number one, at iteration number one, the validation accuracy is 46. At iteration number two, the validation accuracy is again 46. Okay. Then at validation, that means at iteration number four. Okay, three it skipped. Four. Okay, I guess that was three only. This is three only, but okay, it gave 50. Fine. Then at iteration number 4, again it is 50. Iteration number 5, again it is 50. So I told that you have to keep patience for only two times. So this was the iteration, I got 50. After another iteration, that is I got 50. After another iteration, I got 50. तो भाई मैंने बोला था दो तक, ओनली टू तक आपको पेशेंस रखना है. मतलब आपने कोई एक इटरेशन परफॉर्म करा, कोई एक एक्यूरेसी यू डिड अचीव्ड, देन आपने को वही वाली एक्यूरेसी फिर से मिल गया, और आपको वो वाला एक्यूरेसी फिर से मिल गया. I told that keep patience twice. Okay. And after these two patients, because I'm getting the same accuracy which I got here, I need to break. I'll not further train my model. Okay. So there was one change which I think I have to include, and I did include it in front of you, that instead of validation loss, I have to put validation accuracy, because this is classification problem and we are monitoring the accuracy. Okay. So here you can see. ओके, दैट वी आर स्टॉपिंग, वी आर परफॉर्मिंग अर्ली स्टॉपिंग। मतलब मेरा तो जो नंबर ऑफ इटरेशंस था वो 20 था, बट आई एम स्टॉपिंग एट 5 इटरेशन ओनली। आई एम नॉट गोइंग टू वेस्ट माई टाइम अहेड, बिकॉज बिकॉज द रिजल्ट्स आर नॉट इम्प्रूविंग, द वैलिडेशन एक्यूरेसी इज नॉट इम्प्रूविंग। वो 50 से बढ़ नहीं रहा है वो। ओके, सो आई विल बी स्टॉपिंग हियर। ओके, फाइन। So this is your early stopping concept. Okay, and you can save the model. Okay, so your model is saved with the name best eras model.h5. So this model is saved the best model during these 5 iterations. The model where validation score was highest and training accuracy was also highest. That model will be saved in my machine. Okay, because I already commanded that kindly save the best model, save a best only true. So the best model will be saved on my machine. Okay, fine. Then I'm going to load my model. Okay, this is how you can load your model, and you can perform the evaluation, model evaluation. You can check what is the validation loss and what is the validation accuracy for this model. So validation loss is 0.98 and the accuracy is zero point 0.5. Okay, so this is how we do use early stopping. So what we have learned from the previous classes so far is how to build an architecture, how to, in architecture development you have seen layers integration, then putting up the neurons, then I've also taught you about regularization techniques in the previous lecture only. I was discussing that regularization. Okay, and very important concept about regularization, there you have included batch normalization and the dropout. Okay, very very important. And now today I have also explained you this early stopping concept. Okay, fine. Now as we continue our class, and the discussion is related to your optimization or the gradient addition. I hope you don't have any doubt so far what we have learned. Okay, so now again I'm coming back to my initial topic, that is optimization. Okay, so what we are doing in the optimization, sir, you have to reduce loss and you have to increase the accuracy. That's what you have to do, sir. Okay, for that purpose, sir, we are using a technique called as gradient descent. Okay, and this technique came from sir maxima minima. Okay, that is present in calculus, sir. Okay, and descent means I need to calculate the minima, because loss should have to be less and accuracy should have to be more. Okay, from minima. And calculating minima means, sir, you have to differentiate your loss with respect to the weight. Okay, or I would say that in case of minima, sir, you did dy by dx, that's what you did with 0. And then so later on, whatever be the values you got for x here, you're getting certain values of x. Then what you are going to do is, sir, double differentiate d2y by dx square and put the values of x which you have got here in the double differentiation. If it is less than 0, then maxima, and if it is greater than 0, then it is minima. That is the concept. Okay, I did explain to you by drawing line also, as what my teachers also taught me during my school time, that okay, it's something like this. You are having a line, you are having a points. Okay, so this is how it goes. Okay, like this. Okay. So if I say that this is plus, this is minus, this is plus, this is minus, this is plus, maxima minima, and so on. Okay, fine. So yeah, that's what we have to do in the optimization. There are many techniques for optimization. Okay, we'll start with stochastic gradient descent. We have to perform the gradient descent, and we'll start with the stochastic gradient descent. Very important concept again. Every concept here is very much important. Optimizers. So we are studying right now optimizers. Okay, fine. So we have to listen this thing and understand very seriously. Stochastic gradient descent. Let me show you what it is. Now, so here is what your SGD. Hmm. Stochastic gradient descent is an iterative optimization algorithm used to minimize the error or the loss function by adjusting weight and the bias. So that's what I told. I need to adjust the parameters. So then only the optimization is successful. Why it has been named as stochastic? Okay, what's the reason? Stochastic, what I have learned, is related to probability. Okay, probability. That means something which is random. यही होता है stochastic तो. Random meaning होता है इसका. So in traditional gradient descent, that's what the line says. We compute the gradient of the loss with respect to all the training examples. Okay, all the training examples, which are computationally expensive. So what we are going to do in stochastic gradient descent, we will select a subset of data. See what it is trying to say. It has been told to you that you have to calculate the gradient. Okay, gradient. Okay, you are having data, and this data is having many points. Okay, so you have to calculate gradient on each and every point. That's what you have to do. Fine. For example, I am available with 1,000 points in a data. My data is having 1,000 samples. Okay. So over these samples, I need to calculate the gradient because training will be performed over the data, and you are going to give this data to the model, and correspondingly we have to adjust the weight and the bias. Okay, that's what we have to do. Fine. So if I take point by point, okay, point by point, if I take, it's a lengthy process. Okay, it's a lengthy process. Fine. And your goal is to come to minima. And if you are considering point by point, it will take time for you to reach to the minima. And since we are studying deep learning, and deep learning says that the capacity of data which is available with you is more. It is not ML, it is DL. So we are not having a small data set, we are having a big data set. And if you perform optimization point by point, it will take time to converge. Converge means to come here at the minima. Okay. So how long we will wait for our training to get finished? That is the question. So they told that, okay, do one thing. You make batches of the data. That's also we have seen in the previous class. Okay, batch. They told that kindly make batch. Okay. In fact, you can make mini batch. Mini batch. Okay. So right now you are saying that, sir, I am having 1000 samples. Can you make batch of 100 each? Is it possible, sir? So you will be having 10 batches where each batch is having 100 samples. So, sir, you do one thing. You will solve a batch, that means 100 sample, then proceed to the another batch, then proceed to the another batch, and so on. Okay. So do perform batch training. Okay. We always such kind of concept we have also studied in operating system in our computer science. You know that whatever be the jobs we do give in a form of a batch. Jobs means the processes. Okay, we give job or the process to the CPU because we never want CPU to sit idle. भाई उसको बिठा के नहीं रखने का, उसको काम करवाना है ना अपन को. तो काम अपन क्या करते हैं, we give the process CPU को कि आपको हम बैच में देना चाहेंगे, आप ये पूरी की पूरी बैच बंडल करके दे दो उसको. अच्छा, यहाँ पर वन बाय वन दोगे फिर वो जाके इट विल सॉल्व, तो बेटर ये है कि आप पूरा बैच बना के दे दो उसको, वो सॉल्व कर देगा. फिर अगली बैच को आने दो, फिर अगली बैच को आने दो. Okay, so batch by batch now you are going to give the data. Fine. So that's what happens in stochastic gradient descent. Okay, and here you can see that we are making mini batch of the examples, typically like 32 का batch बना दिया या 64 का बना दिया. Here we can see 32, like here. Okay, here like 32. Okay, 32, then 64, 128, and so on. That's what we can do. Submit the data in a form of a batch. Okay, and then compute the gradient. Okay, here is the gradient. The gradient is in the direction of the steepest. Okay, steepest. Actually, क्या होता है gradient? If I do calculate na dy by dx, okay, so that is in a steepest, but putting minus sign will change its direction. So it will be converted into descent. तो gradient तो steepest होता है. Okay, but I will be putting a minus sign so that it should be in a decent format. Okay, because my goal is to minimize the loss, not to increase the loss. And decent as usual. Okay, it indicates that the algorithm aims to move in the direction opposite to the gradient. So whenever some question asks you what is this, why we are calling it as gradient descent, gradient to steepest hota hai upar ki taraf, so you will say that okay, yes, gradient means in the above direction, but we are putting a minus sign in front of it, so it will convert into descent downward because we want to decrease the loss. Okay, and SGD आपने कहा यहाँ कि इस algorithm में, इस टेक्निक में आपने कहा कि सर we will create batches, so batches will help us in faster conversions. That means they will update the model parameters frequently, and faster convergence means I will be quickly getting my minima point. Okay, fine. Regularization, that means mini batch can act in a form of a regularization that can prevent overfitting also. That's what they are saying. We can have parallel processing also. Okay, because you are dividing the data into batches. So if you are having multiple processors, so you can submit the data to each and every core, and that can quickly solve your problem. Okay, and the stochastic nature can help your local minima also, because we don't want to get stuck in a local minima. As I already told you that there are many minimas present. Okay, and if you stuck in any of the local minima, there are rest of the minimas which your model can go, but you are stuck at some place. Okay, so in this particular thing now, you are not going to improve if you are stuck. Fine, so they are saying that the stochastic nature, that means a random nature, okay, is helping you to escape from such kind of points also. Okay, so this is stochastic gradient descent. So let me talk again about it. Okay, let me clear more about the stochastic gradient descent. See, what it is saying that SGD, stochastic gradient descent, it is an optimization technique. Okay, you have to reduce the error or the loss here. Okay, you have to perform gradient descent. Okay, fine. So they are saying that, okay, you are having data, so kindly divide data into batches. We're not going to take point by point because it is a lengthy process. So what we are going to do is, we are considering a batch of data, and in this particular batch, whatever be the data points are present, we will solve them individually. Remember one thing, remember one important thing: though we are building batch, it doesn't mean that you are ignoring solution of a single point. No. Now model will interpret that, okay, I am having 32 data points. Okay, this is one batch which is submitted to me. I'm having 32 data points. So let me solve these 32 data points and finish a batch. That's what it will do. Okay, so we are having a process. Okay, we are having a process. They are having multiple process actually. We are having multiple batches here. Okay, and if I am available with many cores or many processors present with me, so I can give a batch to one of the core, okay, CP1. Another batch can be submitted to another processor, and so on. They will get parallelly executed. But remember one thing: a batch is comprising of data points. So all the data points in that particular batch will be solved. Okay, instead of taking one point by one point, we have converted data into batch. But remember, still considering data into batch, still you are solving point by point. लेकिन पूरे का नहीं कर रहे हो अब आप एक बैच का सॉल्व कर रहे हो. वो जब सॉल्व हो जाएगा फिर आप अगली बैच को सॉल्व कर लेना, if you don't have any other course available. If you are having parallel course, multiple course, so you can submit this data to various course, they will solve them. वो उसको कर देंगे. ठीक है, दैट्स व्हाट आई एम सेइंग. ये क्विकर क्यों है, व्हाई इट इज फास्टर प्रोसेस? बिकॉज ऑफ दिस रीजन ओनली. ओके, इफ यू आर हैविंग 4 कोर्स इन योर सीपीयू, ओके, फॉर एग्जांपल 4 कोर्स आर अवेलेबल, क्वाड है आपका, तो एक बैच आपने इसको दे दिया, एक बैच आपने इसको दे दिया, एक बैच आपने इसको दे दिया, एक बैच आपने इसको जो है वो दे दिया है, दे विल सॉल्व इट. ओके, एंड देयर नेम इज सकोस्टिक इन नेचर. सकोस्टिक का मतलब मुझे और भी ये लग रहा है, दैट्स व्हाट दे सेड, दैट यू आर गोइंग टू मेक अ बैच ऑफ लाइक फॉर एग्जांपल 16, 32, 64, 128 डेटा पॉइंट्स. मुझे एक बात ये भी लग रही है कि यहाँ पर रैंडम सिलेक्शन होगा डेटा पॉइंट्स का. ओके, रैंडम सिलेक्शन. That means you are having a entire data set available with you. Okay, this is your data set. Let me show you that this is your data set. Okay, and it is having so many rows available here. So stochastic means it will pick any of the row to make a batch. For example, this and this row will be part of batch 1. This and this row is coming in batch 2, and so on. तो वो जो बैच बना रहा है ना, वो रैंडम सिलेक्शन करके बना रहा है, रैंडम सिलेक्शन ऑफ द डेटा पॉइंट्स करके बैच बना रहा है. और जो वो बैच बन रही है उसमें इट इज हैविंग 32 पॉइंट्स और 64 पॉइंट्स और 160, लाइक 64 पॉइंट्स और 128 पॉइंट्स एंड सो ऑन. ऐसा करके बना रहा है और फिर वो सॉल्व कर रहा है उसे. दैट इज कॉल्ड सकोस्टिक ग्रेडियंट डिसेंट. और फायदे क्या हो गए ऐसे काम? व्हाट आर द एडवांटेजेस? एडवांटेजेस आर एज लिस्ट एज आपने देखा भी था वहां पर. उसने कहा कि क्विक हो गया हमारा प्रोसेस. Okay, it is quick, and we can skip the local minima also. यदि कहीं आपको अटका रहा है वो, okay, आपको जो है लॉसेस कम नहीं करने दे रहा है, तो यहाँ से अपन इसको स्किप भी कर लेंगे. फाइन. And this is also a regularization kind of a technique. Okay, here you can see. Okay, रेगुलर, ये ओवरफिटिंग से भी बचा लेगा आपको, फास्टर जो है सॉल्व हो जाएगा, पैरेलल हम कर सकते हैं, एंड मिनिमा जो लोकल है उसको स्किप कर दें. So this is what your stochastic gradient descent. Fine. That's, and here is your formula. The same formula as I have shown you previously. Okay, that is W dash is equal to W dash is equal to W minus alpha del L by del W. Some places it has been written like this: theta dash is equal to theta minus alpha del L by del theta. Okay, so theta is actually a parameter which can be weight or a bias. Okay, so don't get confused. Okay, same ही है वो, don't get confused. Fine. So ये आपका stochastic gradient descent है. Okay, fine. And yeah, this is the loss function. Okay, mean square error I already told you. Okay, and if you want to solve a problem, for example, here an SGD algorithm has been mentioned, and in this SGD algorithm, m equal to 0, b equal to 0. That means they are saying that the weight and the bias are 0, initial learning rate is 0.01, and I'm going to perform the optimization until I'm going to get convergence. Okay, and this is how, that means now randomly select a data point from the data set. That's what they are saying. Randomly select a data point from a data set, calculate the gradient. It is saying that okay, calculate the gradient. This is how it's calculating the gradient. Okay, and update the value of your parameters m and b. So calculate the gradients and update the value. Okay, and then later on, here they have given a sample data over which we have solved a problem. Okay, for example, these are the data points. Okay, and these are the initial weight and the bias. Okay, and I'm selecting a random point from this, that is 2 3 4 5 6 7. I'm selecting here as 4 5 as one of the random point. Here I'm calculating the gradient. This is a formula for the gradient. Okay, del L by del W. Okay, here I'm calculating the gradient, and then the formula for the gradient, as you can see from above, is this thing. Okay, minus yi minus like mx plus b into xi. How we got this particular formula? How we have achieved this thing? Del j by del m equal to minus yi minus mx plus b into xi. How we have achieved this formula? Yes. Okay, so if you want me to do the derivation, I can do the derivation. Okay, okay, let me show you here how we have achieved this formula. See, you know, the error or the loss is written as summation y predicted minus y actual ka whole square divided by n. This is how the loss or error is written. Okay, I need to differentiate it with respect to m or weight, whatever you want to say, you can. So here you can do is L equal to summation y predicted minus y actual. Y actual is wx plus b. This is y actual. Okay, wx plus b. That's what you know, na? wx plus b तो होता है जब वो एक न्यूरॉन से, okay, when we give an input to the neuron. Let us suppose x is an input given to the neuron. The neuron is having weight w. So w और bias इसमें ऐड कर दो तो ये हो जाता है ना wx plus b. So that's what I'm writing. That let us suppose the output is wx plus b. Fine. Then what I need to do here is I want to differentiate. Okay, I want to differentiate del L by del W. That's what I need to do. So if I differentiate this thing, you can know that it differentiation ना पहले power का होता है. So power will come in front. So 2 by n summation, let it be yp minus wx plus b. ये ऐसा की ऐसा ही रहा. डॉट, अब पावर के बाद जो है फिर हम अंदर जाते हैं ब्रैकेट के, तो yp का डिफरेंशिएशन विल बी 0 माइनस ऑफ डब्ल्यू एक्स का डिफरेंशिएशन, बिकॉज वी आर डिफरेंशिएटिंग इट विद रिस्पेक्ट टू डब्ल्यू, तो मेरे पास सिर्फ x बचेगा. ओके, माइनस एक्स, और बी का डिफरेंशिएशन जीरो हो जाएगा, बिकॉज यू आर डूइंग अ पार्शियल डिफरेंशिएशन ना। तो व्हेन यू आर पार्शियली डिफरेंशिएटिंग विद रिस्पेक्ट टू जीरो, तो बी 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 जीरो हो जाता है ना। डब्ल्यू से करोगे तो बी जीरो होगा, बी से करोगे तो डब्ल्यू जीरो होगा। सो दिस इज व्हाट यू आर गेटिंग। और उसने जो है इसी बात को लिखा है यहाँ पर। if I remove or if I ignore 2 by n, if I ignore this thing 2 by n, तो मेरे को मिलेगा yp minus wx plus b minus x. And that's what they have written. देखो आप चेक करो, ये माइनस ऑफ वाई आई माइनस एम एक्स प्लस बी इंटू एक्स आई, यही है। ओके, सेम थिंग आई गॉट फ्रॉम द डेरिवेशन। ओके, ये मिला है मेरे को। एंड यदि आप बी के रेस्पेक्ट में इसको डिफरेंशिएट करोगे ना, तो आपको अगेन ये मिल जाएगा, ये इफ यू डिफरेंशिएट इट विद रिस्पेक्ट टू बी, यू विल गेट दिस थिंग, ये। बस वहां एक्स नहीं आएगा, ठीक है। तो ये आ गया। देन आई हैव अपडेटेड माय पैरामीटर्स, आई एम गोइंग टू टेक द वैल्यूज ऑल्सो। ये मैंने वैल्यू आई हैव पुट इट हियर इन द gradient calculation. Okay, I have put here. Okay, and then this is how I updated the value of m and the b. बस ये हो गया, ठीक है। That's it. This is acoustic gradient descent. And I have made a code also for you. Okay, so that you can understand stochastic gradient descent. This is the code for you. So import numpy as np and take a sample data. Here I am having 3 data points: 2, 3, 4, 5, and 6, 7. So stochastic, as I already told, random sampling, randomly कोई सा भी data point वो pick up कर लेगा. Okay, so out of these points 2, 3, 4, 5, and 6, 7, it will pick any of the point. Here I am giving the learning rate as 0.01. Okay, and the number of iterations is 1000. The concept of learning rate, I hope you already know. I have taught you the concept of learning rate. Okay, I will re-explain it ahead as per the requirement. Okay, if it will come. Okay, so in case of learning rate, what we seen in case of LR, that learning rate is a step size. Okay, learning rate is a step size. Okay, and what step size it is? What step size it is? It is your that means coming from a point to a lower. Okay, so how much jump I will be taking? That will be the step size. How much jump I will be taking? That is the step size. Okay, so that is the learning rate. Learning rate is a very important parameter. Very important. Okay, you have to come down, that's what we know. But how much steps you have to take? How much steps you have to take? Either you are going to jump from this to this directly, so this is not an option. You have to take steps. Taking steps means the updation of weight and the bias is reasonable. For example for example initial weight is w. After updation, let us take it 10. After updation, the weight will become 10.1. We never mean that, sir, the weight is 10 right now, and after updation it will become 20. No, ये गलत है, ऐसा नहीं होता. This is not possible. Okay, this will give random fluctuation. Okay, this is fluctuation. That means somewhere my point is someplace and somewhere it is someplace. No, I want I want learning. I want to have a proper training. For that, I want that my point should come in a optimal way rather than to jump. So this is the learning rate, and learning rate is smaller. Learning rate is smaller means I am with the learning rate I am going to control. That's what the word I want to choose here to speak. Control. Control. Learning rate is to control how much adjustment you can do with the weight, how much adjustment you can do with the parameters. So learning rate is a control. Okay, that how much jump you can do to get another point, another weight, another parameter. Okay, so here the learning rate is been taken. एस 0.01 यही होता है, ऐसी ही कुछ वैल्यू होती है. Okay, just like that only. 0.01, 0.02, something 0.001. This will be the learning rates. Okay, never take high learning rate. Okay, तो ये numerical हो गया. Fine. So, so we were studying gradient descent, stochastic gradient descent. I told that, and in stochastic gradient descent, you can make batches. Okay, so to solve the problem in a quick way. Fine. So the term batch refers that the entire dataset. This means that the gradient is calculated over all the training examples in the dataset before updating the model parameters. Okay. So batch refers to entire dataset. That's what they say as a batch. If I do talk about batch gradient descent, not stochastic. If I do talk about batch gradient descent, so it is like a considering the entire data as a batch. Then if I say mini batch, in case of mini batch, I am going to make a subset. Okay, so in case of stochastic gradient descent, we are converting this batch into mini batch. Okay, like 32, 64, 128 data points. Okay, fine. And what happened is, in stochastic gradient descent, if we do consider mini batches, okay, so that is something advantage, like balance between computational efficiency and stable updates. We can get a stable updates with that. Okay, we are having reduced noise than not considering the batches. Okay, the most important thing here is, in case of SGD with the mini batches, we are looking forward for quick convergence. Okay, and I told that if you're not considering the data into mini batches, for example, they told batch means entire data. For example, don't confuse with the word batch. Let us say if I consider the entire data set, so I need to solve on each and every point. If I say entire data set, solve on each and every point, that is not good. It will take long time. So better to divide data into mini batches. Okay, and we were solving, that means I'm showing you this code, that how to solve this SGD part. This is a learning rate. These are the number of iterations I want to work upon. And initially, my weight and the bias are empty. That means 0. Empty means I'm not going to give any value. Initial my weight and the bias are 0. So what I'm doing here is, for I in range, number of iterations. For example, let us iterate for 1,000 times, and and randomly select a data point. I randomly select a data point from here. Any of the data point I will select. Okay, any xn, xi, yi I am going to select from these three. Okay, any of the data point is selected. After selecting the data point, I am calculating the gradients. The same formula as you have seen in the white sheet, the notes, same thing. Here, compute the gradients, and after computation of the gradients, kindly update the parameters. That's it. Okay, if the parameters, and I'm going to print the parameters after every 100 iteration, not for each iteration, I'm not printing. Okay, at every 100 iteration, I'm going to print the parameters. So that's what they did. From iteration number 0, the parameters are zero point 0.2 and 0.05. Then at 100, these are the parameters. At 200, these are the parameters, and so on. So we are printing the parameters after each and every iteration. This is SGD, stochastic gradient descent. Okay, fine. So what we have seen so far, let me summarize the concepts. Okay, let me summarize it. In optimization, we are right now dealing with a technique that is called as SGD, and they told that, okay, you can handle a data, fine, that can be given either in form of a batch, that can be given either in form of a mini batch. If you are giving data in a form of a batch means entire data set. That's what they are saying. For example, you are having 1,000 samples, 1,000 points, so give 1,000 in one go itself. And if you're talking about mini batch, then you are going to divide, or you are going to create sub samples of 1,000. Let us suppose you are creating 100 samples each. Okay, so there will be 10 such kind of samples, or 10 such kind of batches. Okay, so they told that if you are using batch gradient descent, that is stochastic batch gradient descent, okay, then you are going to consider point by point, but it's a lengthy process. Okay, here here learning can be good because you are considering each and every point, fine, but it is like because it is taking time, so computational complexity will be like more. But if you are dividing data into batches, and then you can utilize your all resources, so complexity will get now reduced. Okay, I'm utilizing all my resources and I can solve it quickly. So this one is quick. SGD with mini batch, this is quick. However, SGD with simple batch, that means considering all the data and solving data point one by one, is a lengthy process. Okay, and the formula here, it's a very simple formula. I have written multiple times. That's what you have to follow. W dash is equal to W minus alpha del L by del W. This is how you are going to update the weight of a neural network. And you very well know that, sir, right now also you created an architecture, very simple architecture you created. Sir, you are having one layer, you are having second layer, you are having third layer, and sir, you are having 10 neurons at these layers, 10 neuron at this layer, 3 neuron at this layer, and sir, there is an interconnection. Okay, every neuron is connected to every other neuron, there's an interconnection. Okay, fine, this is a neural network. At the end you are going to get the result. Fine. And every neuron is having the weight, which you are looking forward to adjust during backtracking. Backtracking. However, you have to use an optimization technique, and the optimization technique which we have seen today is stochastic gradient descent. Okay, so here in case of the code which I am explaining, यहाँ पर ये training हो जाएगा. Okay, after the training, if you want to show the plots, you can show the plot also. ठीक है, ये plots हैं. Okay, this is the plot M0 B0, and this is your line. Fine. Then at the 100th, okay, iteration. Okay, now again at the 100th iteration, this is 100 iteration. Now it's been like this, and so on. ये plot कर दिया मैंने. Okay, so in plotting what I did, let me show you that also. प्लॉटिंग में मैंने एम बी और डेटा पॉइंट जो है वो रखा है. ओके, एंड आई एम मेकिंग अ स्कैटर प्लॉट. Okay, so the code is all same, considering the same data, considering the parameters, initializing the parameters, and plotting the line where I'm considering the M and the B and the data point and the title. That's what I'm giving. Okay, तो ये x जो है मेरे पॉइंट्स हैं, y मेरे जो है ये आउटकम्स हैं. ओके, एम एक्स प्लस बी ये मेरा आउटकम्स हैं. ओके, तो वट एवर बी द m एंड द b अपडेट मुझे मिल रहा है, आई एम गोइंग टू पुट इट हियर इन दिस इक्वेशन. तो उससे आई एम कैलकुलेटिंग द वैल्यू ऑफ वाई, तो वो लाइन चेंज हो रही है, आपको दिख रही है लाइन चेंज होते हुए. दैट्स इट, बस और कुछ नहीं है. फाइन. सो ये पूरा ऑल द इटरेशंस 600 700 800 900 ये आपको पूरा मिल जाएगा. एंड यू कैन सी दैट कि ये पॉइंट मैंने कनेक्ट कर लिए. ओके, तो मेरी ट्रेनिंग प्रॉपर हो गई. आई कनेक्टिंग दीज पॉइंट्स. ओके, सो माई ट्रेनिंग इज good with this. So this is acoustic gradient descent. A very simple approach. Don't forget any of the point which I told you in this class. Okay, that means that ये एक optimization process है. This is an optimization process where it accepts the data. Data यदि batch में ले रहा है तो एक एक data point को solve करेगा. Mini batch में ले रहा है तो जितने का आपने बना के दिया उनको solve करेगा, and एक एक करके वो batches को निपटाएगा. That's what it will do. ठीक है, fine. That's all the concept for today. which I want to teach. Okay, let me stop sharing the screen. Let me